So generally speaking, if you're a graduate student, those are pretty accurate as to, I mean, there wouldn't be much of a curve here. 90 to 100 would be an A, 80 to 89 would be a B, 70 to 79 C, 60 to 69 would be a D. For undergraduates, that's going to pretty much hold for the 80 and 90, but probably would go down to about 65 for a C. But again, it's not really, the curve doesn't really apply to this midterm. It's going to be at the very end because homeworks always pull grades up, and therefore you can afford lower midterms and finals because the homeworks tend to pull your overall grade up. So I'm only going to go over parts of the test. I'll post the test and the solutions later today. There is only a few problems that really gave people difficulty on the exam. Whoops, not sure why that's doing that, but at any rate, a couple of them a little bit surprising. So, a bunch of you confuse seek time with rotational latency. So, the seek time is the time it takes for the read-write arm to move to the appropriate track. The rotational latency is the time required for the appropriate block of a disk to move under the read-write arm. So that's rotational latency. Seek time is the movement of the seek arm to the appropriate track. Rotational latency is the time then, once it's at that track, for the disk to rotate under the read-write arm to the appropriate block. A lot of you missed 3. So the DDL is the relational model. Relational calculus is the formal basis for the DML. A lot of you circled relational calculus, but that's the formal basis for the DML. Okay. On 7, this was the most missed problem on the exam. So most of you circled D, which would be correct if race course were in fact a large relation. But if you look at the end of the exam, actually this is the solution so it doesn't have it. Let's see if I can get the midterm. Whoops. Look actually at the midterm, it said the race course relation, there are about 50 race courses. So in fact, with only about 50 race courses, and if you look at how big the race course thing is, it's not going to be probably much more than 100 bytes, so you're only going to be getting that thing into 1 to 2 blocks. So it's just too small. The entire relation is too small for indexing. Yes? Well, usually if it's going to be 2 blocks or less, for sure, it's going to be too small. Because if you have an index, then you'll have to have one access to the index and one access to the disk. And so that's 2 disk accesses, which is the same as having 2 blocks. So usually the rule of thumb is 2 blocks or less is not enough for indexing. Okay. And in this case, certainly 1 block is definitely too small for indexing. But generally 2 blocks or less is what I would say is too small for indexing. Okay. This was a good page. Almost everyone got everything on this. 12, a bunch of you selected one to many rather than many to many for the degree of the relationship. So the degree of the relationship takes the maximum cardinality for each entity in the relationship. And in this case, the maximum cardinality of each of them is star, which makes it a many to many relationship. So when you're asked for the degree of the relationship, you're being asked for the maximum cardinality of each entity in the relationship. If you're asked for the multiplicity of the relationship, that's actually meaningless because it's actually doesn't apply. Multiplicity does not apply to an entire relationship. Multiplicity only applies to each entity in that relationship. So you would actually, if I was asking a question about multiplicity, I would have said, what is the multiplicity of course? And then you would have answered 1 to many. But you talk about, so we talk about the multiplicity of a single entity. We talk about the degree of a relationship. Okay. 14. Many of you chose A, which is set intersection, rather than D for the relational algebra operations that form a join. A join is a Cartesian product with a selection applied to it. So that was D. A is actually set intersection. That describes set intersection. And B and C are kind of meaningless. Neither of them describe set division. I just came up with garbage for those. Okay? And C is meaningless. It actually would be syntactically wrong. You can't have a selection operator as a binary operator. So actually C is absolute syntactic garbage. Okay, most of you getting these. 16 through 19 were actually the best problems on the entire exam. Almost everyone got the SQL and relational algebra queries, so that was good. Almost everyone got 20. On 21, some of you thought join was fundamental. It's not. Some of you thought set intersection was fundamental. It's not. You can get set intersection from set difference. You can get join from Cartesian product and select. So usually, at most, there was 1 point missed on this problem. Most of you got 22. So 23 then, the normalization, whoops, most of you got 23. And then 24 through the normalization problems gave you all some problems. So you were given a restaurant, basically a set of orders. So the universal relation was a set of orders. And you were given some functional dependencies. You were given the primary key. And you were told what the entities were. Okay, I want it to be very clear that tables and chairs were not entities. So that would help you with the next problem, which was the table is susceptible to various types of anomalies. So I had an example, it turns out, of an insert anomaly, a delete anomaly, and a update anomaly. And the first ones were what would be potentially delete anomalies. A delete anomaly can only occur on an entity. And menu item was of the two choices you basically had for delete, only a menu item is an entity. B, an order is not an entity. An order is, what do you think an order is? It's a relationship. Okay? So just because you delete the last order, it doesn't matter. Okay? And a chair is not an entity. Okay? That's why I specifically told you what the entities were. Chair is not an entity. Okay, then the changes, you had 3 possible changes. So if you change the quantity ordered, you must update every instance of that quantity ordered. Well, every quantity ordered is unique not unique, but is specific to the order. So if you change it for one order, it's not going to affect any other order. The quantity ordered is specific to each order. However, if you change a menu item's description, then you must change it everywhere because that doesn't change from order to order. It's the same, should always be the same. And then it's true, if you change a restaurant number, you must indeed change every instance of that restaurant number. So that is true. You'll have an inconsistency if you don't. But restaurant number is a what? Foreign key. Okay, and it's also part of the primary key. When it's part of the primary key or a foreign key, it cannot be an anomaly. Okay, we can't do anything about redundancy with foreign keys and primary keys. That's the way it is. We have to try to keep them consistent. So a change anomaly only occurs with non-key items. That's why E is not correct. And finally, you had 3 insertion things. So the only right one was a new restaurant. You can't insert a new restaurant unless it already has an order associated with it, because a restaurant is an entity. So a table is not an entity, therefore it doesn't matter that you can't insert it. And an order is a relationship, and yes, it has to have a chair, table, and restaurant number associated with it. That's a business rule. That's not some kind of anomaly. You can't put in an order unless someone's placing it. So it's nothing wrong with requiring that information in H. So questions about that? Okay. Then on the functional dependencies, you were asked to identify how they would be used in a normal form decomposition. And there were 3 possibilities: that it could be used to go from first to second normal form, in which case it's a partial dependency. B was it could go from second to third normal form, in which case it's a transitive dependency. And C, it might not be used because the dependency represents a candidate or primary key. So if it's being used to convert from first to second normal form, then the determinant must be a subset of the primary key. It must be a partial dependency. So the ones that you see with A, all of their determinants are strict subsets of the primary key. So they are partial dependencies and are used to convert from first to second normal form. Credit card number is determined by this relationship, and it's on the right-hand side, and then credit card number determines cardholder name, so it is a transitive dependency, which is B. And then this one right here that's marked C, that was the dependency involving the primary key. The determinant for the one labeled C here, that determinant is exactly the primary key. It's not used in the decomposition because it represents a primary key. Okay, moving on. I know, so undergraduate students, for a moment you can tune out, although it wouldn't hurt to listen to what I have to say. Most everyone got the first problem with the printing the name of each runner and their average time. Most of you grouped by runner name, which was fine. I didn't tell you runner name was unique, but I didn't think it was something I wanted to quibble over. Ideally, you would have grouped by runner number, which is unique, and runner name. By grouping on the runner number, you guarantee uniqueness, and by adding runner name to the group by clause, you're allowed to use it up in the select clause. So some of you that just grouped by runner number got 1 point taken off, and that's the reason. Technically, you can't have runner name up in the select clause unless it's down in the group by clause. Then on the relational calculus, y'all did surprisingly well on it because it's tough. The one thing some of you forgot is that free variables are ones that occur in the result list. So in this Winnie the Pooh example, I wanted to print all basically information about the race and results of Winnie the Pooh, which I could get from two relations, the race relation, which I've labeled RA, and the result relation, which I've labeled result. Since those two relations appear in the results list, they must be free variables. They can't, they can't be bound. So they can't be bound. Runner is not appearing in the results list, but it must be used in the so-called join in order to find the races that Winnie the Pooh ran in. So runner is actually the bound variable here. So we range over the race and race result relations and then say there exists a runner such that the runner's name is Winnie the Pooh, and then we have the joins that are required to find the race and result information. So the biggest miss here was simply not realizing which variables were free variables and which variables are bound. So again, the rule is any variable appearing in the result list must be free. Any variable not appearing in the result list is going to be bound by an existential quantifier. Okay. Then on the ER diagrams, there was kind of a bunch of missing on this. Many of you overthought this one. So if you look at the relations, here's the relations. And you can pretty much draw the ER diagram from these relations. So as long as you can identify which relations are the relationships. The relationships here are race staffing and race result are the two. The other five relations, runner, race course, course segment, race, and volunteer, are entities. So if in the ER diagram you have these five entities, then the race staffing is really volunteer staff's race, and the race result is really the runner runs in race. So you're looking at it, this is really the race results relation, and this is the race staffing. Now you see a couple other relationships here. So if you look at course segment, you see that course segment has a course number as part of its primary key. That's also a foreign key. And course segment is what kind of entity did we call course segment? Weak. It's a weak entity. It depends on the existence of a race course. So a race course has course segments. And then if you look at race, you see that race has a course number in it, which makes it a foreign key. So a race course hosts a race. And generally, you draw the arrow toward the relation or entity that has the foreign key. So race had the foreign key for course, so the arrow is pointed toward it. Course segment has the foreign key, so race course has the edge pointing toward course segment. So many of you decided that race should be a relationship, and I can understand why, because many of my exams have a ternary relationship. But the key, and I only took off a couple points for saying that race was a relationship. But the reason it's not really a relationship is the whole thing depends on races. Without a race, there's really no database. Okay? So race is actually an essential entity here. The whole race database is like the planets rotating about race, which is the sun. The sun is if in some sense, sun is the only strong entity in this entire database. Everything else goes away if you don't have a race. So it's not a relationship. It actually is the strongest entity in this database. The relationships are all pretty much independent. So volunteer and runner don't really have much of a relationship. It's not like Brad Vander Zanden runs in a race where Nick was a volunteer, because there's lots of other volunteers that were also volunteering for that race. So when you have more than a two-way relationship, it's because there's a strong tie between the elements in that relationship. Like in the restaurant relation that I had earlier, okay, there I showed a three-way relationship, and that's because an order fundamentally is between a customer, a restaurant, and a menu item. Okay, it involves all three. You can't get away from that. But a race has essentially independent relationships with a race course. So the course on which the race is run really is independent of the runner and the volunteer. The runners that run in the race don't affect who volunteers. Who volunteers doesn't really affect who runs the race. So those are independent. Okay, so there was just a little bit of overthinking that went on this problem. The other common miss was forgetting about course segment. Okay, course segment is an entity, and race course consists of multiple segments. And then most of you got the binary search tree. The biggest issue was ignoring what I said in class and what I said on the exam, which was to put the odd number of keys in the leftmost node. Okay, so many of you stuck, not many of you, but some of you stuck 40 into the right leaf. Okay, but that's not correct. Okay, based on what I told you, so you got a couple point deduction for that. Okay, so any questions? If you have something personal about your exam, I'll be happy to answer it after class. I have the solutions posted later today, not right after class, but later today. Whoops.